Hi folks, welcome back. I hope you're all doing well. Today I want to take a look at a paper that came out just about a week ago, and it's interesting because it looks at an entirely new class of side channel attacks. The authors here focus on the x86 architecture, so chips made by Intel and AMD, but the basic idea should carry over to any chip that supports dynamic frequency scaling. A side channel attack works by observing some fundamental physical property of a computation. So, for example, if an attacker could observe timing differences or power consumption differences based on patterns of data or patterns of instructions being executed, and that observation allowed the attacker to extract information about the computation, that would be a side channel attack. In recent years, this has become a very well-known field of study because we've had several very hard to mitigate side channel attacks, things like Spectre or Meltdown, which relied on very fundamental parts of the microarchitecture of modern chips, things like how their caches work or how branch prediction works on modern chips. And now this paper looks at yet another physical property of the chip, which is the frequency at which it is running. But the authors go much further than that and even demonstrate how this side channel attack based on frequency scaling can actually be exploited by a remote attacker. So what is frequency scaling? It's a feature that is present in almost every modern chip, and it allows the chip to change the frequency at which it is executing. And why would you want to do that? The goal is to achieve some sort of balance between performance and power consumption while also staying within the overall thermal envelope that the chip can operate within. Now, sometimes this frequency scaling happens automatically, but there's another mode where the operating system can explicitly control this frequency scaling. With all the complexity of most modern chips, they lean more towards controlling this frequency entirely automatically based on things like the power consumption, the number of cores being used, and so on. One very common way in which this is seen is under a sustained heavy workload, the chip will often kick into some sort of turbo mode where it reaches a high frequency, but it cannot sustain that because it gets hotter and hotter. And so after some time, the chip will scale back to a slower frequency. So that's step one in the attack, the fact that chips will automatically change their frequency based on the workload. Step two of this attack depends on the physical fact that the power consumption of the chip depends on the data that it is processing. This is commonly modeled using two different models, the Hamming weight model and the Hamming distance model. In the Hamming distance model, the power depends on how many times bits flip, so 1 to 0, 0 to 1 during the computation. In the simpler Hamming weight model, the power consumption only depends on how many bits are 1. Let's look at a very simple example of how the workload affects these frequencies. The authors took two benchmarks, one which only uses int32s and another one that uses floating point numbers. The int32 benchmark is the lighter load, and you can see that when running that, the chip can sustain a higher frequency for much longer before it gets kicked down to a lower frequency due to hitting its thermal envelope. So that was a very simple proof of concept that shows that the way dynamic frequency works in terms of how long the chip can hold the fastest frequency and when it kicks back down to lower frequencies depends on the workload. And that means that observing this kind of dynamic frequency scaling can conceptually leak information about the workload being run on the processor. This is the central idea of the paper, and then the authors go on to build on this to craft a very precise attack. Now let's go one step further. How can we actually try to peek at secrets? How can we actually distinguish data based on frequency scaling? And here again, the authors do a very simple experiment where they execute one instruction, in this case, a shift left instruction, repeatedly on the same data. But they do it for different kinds of data with different Hamming weights. And you can see in this graph how, depending on what the Hamming weight of the input data is, the chip is able to hold its top frequency for different amounts of time. And when you plot them out on a graph like this, you can clearly distinguish when the chip was executing this shift left instruction on data with Hamming weight 16 versus, say, Hamming weight 32. So now we've gone from being able to distinguish between workloads to being able to distinguish between the data that the workload is operating on simply by observing how the chip scales its frequency. The authors go on to do a number of experiments to validate the Hamming distance and the Hamming weight model, and they do indeed find that larger Hamming distances in the data that the chip is operating on lead to higher power consumption, which in turn means that the steady state frequency will be lower for sustained workloads. They also find a similar result for the Hamming weight of the data being operated upon. And then they go on to construct an actual attack. This is a chosen ciphertext attack, which means that the model is one where an attacker is free to send as many encrypted pieces of data as they want, and they can observe the plain text being sent back. And the goal of the attacker is to figure out the secret key that is being used to decrypt these chosen ciphertexts. This is the part of the paper I'm going to gloss over, but if this setup sounds intriguing to you, I'd really encourage you to read the paper for the details. What can we do to mitigate these attacks? One obvious technique is to simply disable frequency scaling. Now, obviously, that is a very blunt tool, and it also significantly reduces the overall performance of the system. There are also software techniques like homomorphic encryption, which would mitigate this because the way it works, it doesn't leak information about the keys that it's using. But this attack is still pretty new, and satisfactory mitigations, other than simply disabling frequency scaling, don't seem to have been identified yet. The authors have done the right thing by giving Intel and AMD a heads up and waiting a period of time before disclosing this vulnerability. And I'm hoping that now that this has been published, this gets more attention and we come up with some better mitigation techniques. So that was a quick look at Hertzbleed. That's what they're calling it because Hertz, get it? Which is a new kind of side channel attack that can remotely extract information about secrets based on the frequency scaling of the chip. I hope you enjoyed that, and I will see you next time. Thank you very much.